Okay. Hello. So looks like most colleges are joined in. So let me start the session today. And sorry, unfortunately, because of some technical issues, we could not have the session on Monday. Nevertheless, let's start our discussion today. So let me just do a brief recap of what we've been doing. We've considered the two antenna wireless communication system. And for the two antenna wireless communication system, that is considering a system with two receive antennas. This is the receiver, this is the transmitter, and H1 is the channel coefficient, H2 is the channel coefficient between the transmit antenna and receive antenna 2, right? And where H1 and H2 are, we said, relay fading coefficients and also independent, right? So H1 and H2 are relay fading, and they are independent, right? And therefore we derive the probability of bit error for BPSK communication. The bit error rate for this communication system, we said the average bit error rate equals, for this system, equals half times 1 over 1 plus half SNR. I hope everyone remembers this, square, where SNR equals P over sigma, SNR equals P over sigma square. And also we said at high SNR this can be approximated as follows. This is approximately half. At high SNR, because SNR is high, so I can ignore this additive factor of 1 in comparison to SNR. Therefore I will get average bit rate approximately equal to half times 4 over SNR square, which is basically equal to 2 over SNR square. And the most important thing to realize here in this bit error rate when you have multiple antennas is that whereas the bit error rate for a simple AWG, a simple relay fading channel with one transmit, one receive antenna, it decreases as 1 over SNR. This bit error rate decreases as 1 over SNR square. You can see this factor of 2 over here, right? So now the bit error rate has decreased. It has decreased from 1 over SNR to 1 over SNR square, and that we saw, if someone remembers, if someone can someone recall what is the SNR that we required for AWGN to achieve 10 to the power of minus 6 bit error rate? What is the SNR required? Can someone prompt me what is the SNR required? Does someone remember what is for 10 to the power of minus 6 bit error rate? What is the SNR that is required? For a bit error rate of 10 to the power of minus 6, what is the SNR that is required? Does anyone remember? Yeah, about 14.19 dB, that is correct. Similarly, in a relay fading channel, correct, I'm getting the answer from several people, very good, correct. For a relay fading channel, what is the SNR required? That is 60 dB, that is very high because it decreases 1 over SNR. And now with two antennas, with L equals 2 antennas, what is the SNR that is required? The SNR that is required is 31.5 dB. So what we have said is something very interesting. We've said basically even though with two receive antennas, when we have two receive antennas across a wireless fading channel, the SNR required for communication, SNR required for reliable communication is coming significantly from 60 dB. It is coming down to 31.5 dB, and all this is thanks to this factor of 2 in SNR for the bit error rate. So previously while bit error rate was 1 over SNR, now the bit error rate is 1 over decreasing as 1 over SNR square. It is decreasing as 1 over SNR square. And what I started out doing the other day was to basically generalize this to a case of L antennas. What my next step was to consider an L antenna communication system. So next, consider a consider a general L antenna wireless system. Alright, so this was our next step, that is we have to consider a general L antenna wireless system. And we look at an L antenna wireless system, also again the steps are very similar, but let me just quickly illustrate what the essential steps are, and so that it becomes clear what is happening. So I have L receive antennas. At the receiver I have one transmit antenna. This is the transmitter. Remember, this is the receiver. This is the transmitter, right? And therefore uh, what I have here is the channel coefficient between the transmitter and the first receive antenna is H1, transmitter and second receive antenna is H2, so on and so forth. I have HL. So I have now L. What I'm saying is I have the total number of antennas I have here. I have L I have L receive antennas. So the total number of receive antennas I have in this system, that is L. And therefore my system model, if I write my system model again similar to what I had written for the two antenna scenario I have, now I can generalize this. I have Y1 equals H1X plus N1, Y2 equals H2X plus N2, so on. YL equals HLX plus NL. So I have the vector YL. If I vectorize this, I have the vector YL equals the vector H bar plus the vector N bar. So what I have here is I have Y bar equals H bar X plus N bar. Only difference now is that Y, H and N are L dimensional vectors. So vectors Y bar, H bar, comma N bar are L dimensional. These are L dimensional vectors, correct? So these are, I have these L dimensional vectors. So what I have is now, because I have multiple receive antennas, I have converted my communication system, my simple scalar communication system, into a vector channel. Now if you look at it, I have L channel coefficients H1, H2, HL. So you can also think as this as a vector communication channel, an L dimensional vector communication channel. Also we are assuming that these noise components N1, N2 and these noise components are, these are additive white Gaussian noise components with mean 0 and power sigma square. That is, each noise component, the noise is Gaussian, each noise component is IID, each Ni is IID. IID means independent identically distributed Gaussian of power sigma square. That is the noise power. Basically what we are saying is that the noise power is sigma square. Alright, so the noise power is sigma square. Therefore, we all went through this for the for the two antenna scenario. We said at the receiver we are going to combine the signals Y1, Y2, YL using the combining weights W1, W2, WL. So at the receiver combine Y1, Y2 up to YL as W1 conjugate Y1 plus W2 conjugate Y2 plus WL conjugate YL. So at the receiver we combine WY1, Y2, YL as W1 conjugate Y1 plus W2 conjugate Y2 plus so on WL conjugate YL. So at the receiver we are combining these things, and we also derived what are the optimal combining weights. What are the combining weights W1, W2, WL to maximize the SNR at the receiver. So the next question that I will ask you is what are the combining weights? What are the combining weights W1, W2, WL to maximize the SNR at the receiver? Can someone tell me what are the combining weights W1, W? How should I choose the combining weights W1, W2, WL to maximize the SNR at the receiver? Right, so W bar, which is the weight vector W bar, equals H bar divided by norm H. So everyone can see we are performing W bar Hermitian times Y bar. This is the combiner. This is equal to W1 conjugate Y1 plus WL conjugate YL, and we need W bar, the optimal choice of W bar equals H bar divided by norm H bar. Here we can see that W bar equals H bar divided by norm H bar. This is also known as the maximal ratio. This is also known as the maximal ratio combiner. Fine, this is also known as the maximal ratio combiner. Therefore, the SNR at the receiver, when I use the maximal ratio combiner, the SNR equals, we have seen norm H bar square P over sigma square equals magnitude H1 square plus magnitude HL square P over sigma square, which equals G1 plus G2 plus GL into P over sigma square, right? So this is the SNR at the receiver, which is basically summation of G1 plus G2 plus so on up to GL times P over sigma square, where each GI equals magnitude HI square. Each GI equals magnitude HI square. Right? You can see that, everyone can see that each GI is gain of each channel GI equals the magnitude of HI square. So each magnitude GI is equal to magnitude HI square. And therefore, what is the instantaneous beta rate? Now this is the SNR at the destination. By the way, this is the SNR, not to be confused with SNR P over sigma square. This is the SNR at the receiver. This is the SNR at the receiver after the maximal ratio combining operation. Therefore, what is the beta rate? What is the instantaneous beta rate? By instantaneous beta rate, I mean what is the current beta rate as a function of the channel gains G1, G2, GL. That is not the average beta rate, but what is the current beta rate for BPSK transmission as a function of the channel gain? This is what is the current beta rate? Can someone tell me? Q of square root of SNR. That is correct. So the current beta rate is Q of square root of G1 plus GL E over sigma square. So this current beta rate is basically a function of the channel gauge G1 up to GL, that is given as Q of square root of SNR. SNR at the receiver, which is nothing but Q of square root of G1 plus so on up to GL times P over sigma square. Okay. And now I can use the Chebyshev approximation for this. Basically the Q of X is approximately equal to, actually it is less than or equal to half e to the power of minus half x square. So using this approximation, my instantaneous beta rate becomes approximately equal to half e to the power of minus half p over sigma square times g1 plus g2 plus g. Hope everyone can see this. Alright, so using the Chebyshev approximation, this becomes half e to the power of minus half p over sigma square g1 plus g2 plus so on until gl. So using this approximation, I'm able to get that the net beta rate for this system is half e to the power of minus half p over sigma square g1 plus g2 plus so on up to g of l. What is remaining now is I have to compute the average beta rate. Is that correct? I have to compute the average beta rate. So next I have to, so this is the instantaneous beta rate, or this is the current BER as function of the channel gains. I have to compute the average beta rate. To compute the average beta rate, I need the distribution of the gains G1, G2 up to GL. We already know what is the distribution of the each channel gain. What is the distribution? What is the distribution of GI? Right? Distribution of each GI as GCT is responding. It is exponential. That is e to the power of minus GI. Further, all the GIs are independent. If all the GIs are independent, what is the joint distribution? What is f of G1 up to GL? That is simply, what is the joint distribution? The joint distribution, since they are independent, is the product of the individual distributions. Therefore, e to the power of minus G1 into e to the power of minus G2 up to e to the power of minus GL, which is basically e to the power of minus G1 plus G2 up to GL. So basically the joint distribution of the G's is e to the power of minus G1 plus G2 up to GL. Several are responding. That is the correct answer, e to the power of minus G1. Therefore now to average this thing, I have to multiply this beta rate, this instantaneous beta rate I have over here with the distribution, and therefore I have to average it. Therefore average beta rate That is basically my instantaneous bit error rate half e to the power of minus p by 2 sigma square into g1 plus g2 plus gl times e to the power of minus g1 plus g2 plus gl, and now I have to integrate. Each gi is from 0 to infinity, so I have L integrals dg1 dg2 so on up to dg. So that is the net expression. That is basically the instantaneous bit error rate half e to the power of minus p over 2 sigma square time into g1 plus g2 plus up to gl times minus g1 plus g2 up to gl and integrate over multiply by dg1 dg2 up to dgl and then integrate from 0 to infinity. Okay, so that is what we get. Basically it is the instantaneous bit error rate. This is the instantaneous bit error rate. This is the distribution, and we are therefore averaging the instantaneous bit error rate over the distribution. We are therefore averaging the instantaneous bit error rate over the distribution. That is what we are doing, right? We are averaging the instantaneous bit error rate over the distribution, and therefore this we already seen. We can simplify this as, basically this can be written as integral 0 to infinity integral 0 to infinity. I can write this as e to the power of minus g1. I can collect all terms corresponding to each gain g1, g2, gl separately, and therefore I can write this as e to the power of minus g1 into 1 plus p by 2 sigma square into e to the power of minus e2 1 plus p by 2 sigma square, so on and so forth, e to the power of minus gl 1 plus p by 2 sigma square into dg1 dg2 into dgl, right? So therefore what we get is e to the power of minus g1 into 1 plus p by 2 sigma square, e to the power of minus g2 into 1 plus p by 2 sigma square, so on, e to the power of minus gl into 1 plus p by 2 sigma square, and so on, is equal to, this is equal to, until so on, and this is equal to, and therefore there is a factor of half also, correct? Thank you for pointing it out. And this now we is equal to, we said this can be split into the product of, because this is a product of factors which depends only on g1, g2 and gl. I can split it into the product of L factors, that is pi. I can write this as the product pi I equals 1 to L, where pi denotes the product 0 to infinity e to the power of minus gi 1 plus p by 2 sigma square p gi, which is equal to half 1 over 1 plus p by 2 sigma square to the power of L, right? So basically this bit error rate that we have seen is half 1 plus 1 by 1 plus p by 2 sigma square to the power of L. This is the bit error rate. What is this? This is basically, this is the average PR for L antennas. And at high SNR, can someone tell me what is that? It approximately equals to, at high SNR, what is the value of this? At high SNR, that is at high value of P by sigma square, at high SNR, what is the value? At high SNR, so this approximation is at high SNR, what is the value approximately? At high SNR, this is 2 over SNR to the power of, at high SNR, this is approximately 2 over SNR to the power of, this is approximately, can someone give me the exact answer? What is this value at high SNR? 2 over SNR to the power of L is not exact. What is the correct expression for the bit error rate at high SNR? Can someone tell me what is the bit error rate at high SNR? What is the correct expression? That is, look at this expression. Can someone simplify what is the bit error rate at high SNR? That is correct. The bit error rate at high SNR, as VCAP is, about some of you are now responding, this is half. I have to neglect this term of 1, the additive factor of 1. So that will give me 2 to the power of L divided by P over sigma square to the power of L, which is equal to 2 to the power of L minus 1 divided by SNR to the power of L, where SNR equals P over sigma square. Therefore, you can see that the bit error rate is decreasing at 2 to the power of L minus 1 by SNR power of L. This 2 to the power of L minus 1, this is a constant, don't worry too much about this. The most important thing to realize here is that the bit error rate is decreasing as 1 over SNR to the power of L. The bit error rate is decreasing as bit error rate bit error rate is decreasing as 1 over SNR to the power of L. With L antennas, the bit error rate is decreasing as 1 over SNR raised to the power of L. With L antennas, the bit error rate is decreasing as 1 over SNR raised to the power of L. Right? Everyone can see that. And this L, so you can see now, so that is why with two antennas, the bit error rate was decreasing as 1 over SNR square. With 3 antennas, it will decrease as 1 over SNR cube, and so on and so forth. And this L, basically, which is the exponent of the of 1 over SNR in the bit error rate, this is known as the diversity order. This is a very important quantity for wireless communication. This L, this is known as the diversity order. That is simply saying, if the bit error rate is decreasing as 1 over SNR to the power of D, the diversity order is D. The bit error rate is decreasing as 1 over SNR to the power of L, therefore the diversity order is L. And what this says is, for an L antenna system, in a system with L receive antennas, the diversity order is basically L. That is what this is saying. This is an important quantity. Let me write it down clearly again. This is basically the diversity. This is the diversity order for the wireless communication system. So this is the diversity order. Degree of, I'm getting a question regarding degree of freedom. Degree of freedom is something different. I will come to that later. This is the diversity order of a wireless communication system. Okay, so this is the diversity order of a wireless communication system. And therefore, what is the significance of this diversity order? How come the bit error rate is decreasing as 1 over SNR to the power? Now, the next couple of minutes, I will basically try to emphasize, try to explain what is the impact or what is the significance of this diversity order. How come the bit error rate is decreasing as 1 over SNR to the power of, how come the bit error rate is decreasing as 1 over SNR to the power of L in an L antenna wireless communication channel? I'm getting a question regarding the optimal value of L. The optimal value of L, there is no fixed value of L. The value of L keeps changing from system to system. For instance, in 4G LTE systems, L can be as high as 4 or 8 antennas. Depending on the L depends on the number of antennas. So the number of antennas, so L basically depends on the number of antennas that are there at the base station and the mobile handset. Okay. Alright, so let us try to understand what is the impact of this quantity. How come the bit error rate is decreasing as 1 over SNR to the power of L in an L antenna system? And the reason is slightly subtle and very interesting. Now, similar to the diverse, remember we did a deep fade analysis. We found out what is the probability of deep fade for a relay fading channel. Everyone remember the probability of deep fade for relay fading. When is the relay fading channel in a deep fade? Does anyone remember? Can anyone prompt me? When do we say that the channel is in a deep fade? The probability is 1 over SNR, that is fine, but when? What is the event corresponding to the deep fade? When do we say that the channel is in a deep fade? Can someone remind me? When do we say that the channel is in a deep fade? When the gain, correct, people are saying, someone is responding, when the received signal power is less than noise power, that is the power at the SNR, signal power at the SNR. For a relay fading channel, we said when mod h square times p is less than or equal to sigma square. Therefore, with L antennas, now can we generalize this? With L antennas, when does with L antennas, when does deep fade occur? Can someone explain to me with L antennas, when does deep fade occur in a wireless communication system? When does the deep fade event, when does it occur in a wireless communication system with L antennas? When does it occur in a wireless communication system with L antennas? Can someone give me an idea using this intuition that deep fade occurs when magnitude h square p is less than or equal to sigma square? When does the deep fade event, do you think? What is the corresponding deep fade event for a wireless communication system with L antennas? So if I have L receive antennas, when does the deep fade event occur? Can someone tell me when does? Of course, the deep fade is when the received signal power is less than the noise power, or the signal power at the receiver is less than the noise power. So can someone tell me, how can we say, when can we say the system is in a deep fade in the wireless system with L antennas? Yes, I think PSG is giving me the correct answer. That is very correct. See, SNR at the receiver, that is norm h bar square P. This is the SNR. This is the signal power after combining, right? And the noise power is sigma square. So we can say deep fade if the noise, if the signal power norm h, if the signal power norm h bar square P is less than or equal to sigma square, right? So we can say deep fade, the system is in a deep fade if my norm h bar square P is less than or equal to sigma square, which means deep fade if norm h bar square is less than or equal to sigma square divided by P equals 1 over SNR, right? Which means system is in a deep fade if G1, remember norm h square is nothing but G1 plus G2 plus GL less than or equal to 1 over SNR. So therefore the system is in a deep fade if norm h square is less than or equal to 1 over SNR. Norm h square is less than or equal to 1 over SNR. So that means that G1 plus G2 plus up to GL is less than or equal to 1 over SNR. So we can say that the system is in a deep fade. The system is in a deep fade if G1 plus G2 plus so on up to GL is less than or equal to 1 over SNR. Alright, so the system is in a deep fade if G1 plus G2 plus so on up to GL is less than or equal to 1 over SNR. Alright, so that means that basically, now let's look at this. G1 plus G2 plus GL is less than or equal to 1 over SNR. That means now also we have, remember what is each GI? Each GI is greater than or equal to 0 because this is the gain, this is the power, this is GI is equal to, remember each GI is equal to magnitude of HI square. So each GI is greater than or equal to 0. Therefore what can I conclude about if G1 plus G2 plus so on up to GL is less than or equal to 1 over SNR, what can I conclude about each GI? What can I conclude about each GI? Can someone answer this question? What can I conclude about each GI? What can I conclude about each GI? Can someone answer the question? What can I conclude about each GI? No, I cannot conclude that each GI is less than SNR over L because I know, all I know is that each GI is less than or equal to 0. What can I conclude about each GI? Therefore correct, each GI is less than 1 over SNR. That's the only thing I can conclude. Each GI is less than or equal to 1 over SNR. Right? It has to be the case, right? Because if each GI is greater than or equal to 0, let's say G2, G3, GL are 0, then G1 has to be less than or equal to 1 over SNR. And this is the minimum value of G2, GL, that is they cannot be negative, right? So in the worst case, if G2 and so on are 0, then G1 is less than or equal to 1 over SNR. So in any case that if the sum is less than or equal to 1 SNR, each GI has to be less than or equal to 1 over SNR. Now therefore, what is the probability that each GI, so now my question is, what is probability each GI is less than or equal to 1 over SLR, which is basically we are saying G1 is less than or equal to 1 over SNR, G2 is less than or equal to 1 over SNR, so on, GL is less than or equal to 1 over SNR. What is the probability? What is the probability of this event? What is the probability that G1 is less than or equal to 1 over SNR, G2 is less than or equal to 1 over SNR, GL is less than. So for instance, let me ask a simpler question. What is the probability that G1 is less than or equal to 1 over SNR? What is the probability? What is the probability G1 is less than or equal to 1 over SNR? That is basically correct. I have to integrate the distribution e to the power of minus G1 from 0 to 1 over SNR dg1, which we said for large values of SNR, if 1 over SNR are close to 0, this is approximately 1 over SNR. So each of these probabilities, probability G1 is less than or equal to 1 over SNR, probability G2 is less than or equal to 1 over SNR, probability GL is less than or equal to 1 over SNR is 1 over SNR. Therefore, what is the joint probability now that G1, G2 and so on until GL is less than 1 over SNR? Is everyone getting the question? The individual probability G1 is less than 1 over SNR, G2 is less than equal to 1 over SNR. Each of the individual probabilities are 1 over SNR. What is the joint probability of the event? That is all of them happen together. That is correct. So the joint probability because G1, G2, GL are independent, that is nothing but the product of the individual probabilities, that is 1 over SNR into 1 over SNR into 1 over SNR equals 1 over SNR to the power of L. Right. Therefore, because, and remember this follows, why does this follow? This follows because G1, G2, GL are independent. This follows because G1, G2, GL are independent. Because G1, G2, GL are independent, correct. Because G1, G2, GL are independent, the joint probability is the product of the individual probabilities, which is 1 over SNR into 1 over SNR into 1 over SNR, which is 1 over SNR to the power of L. Therefore, what we are seeing is that the probability of deep fade is 1 over SNR to the power of L. And therefore, since the probability of deep fade is decreasing is 1 over SNR to the power of, remember for the Rayleigh fading channel, the probability of deep fade is 1 over SNR. Now it has become 1 over SNR to the power of L. Therefore, since it has become 1 over SNR raised to the power of L, the probability of deep fade is decreasing is 1 over SNR to the power of L. The corresponding bit error rate is also decreasing as 1 over SNR is to the power of L. Probability of deep fade decreasing as 1 over SNR to the power of L, and therefore the corresponding bit error rate right? So the probability of corresponding bit array. So we are seeing, basically what we are seeing is basically the probability of deep fade is decreasing as 1 over SNR to the power of n. What is the intuition behind this probability of deep fade decreasing as 1 over SNR power of n? Let me go back and let us look at the figure. When I have L antennas, let us look at the figure corresponding to L receive antennas. Right. Now previously what we said is in a single antenna system there is only one link. However, in a multiple antenna system there are L links. We have link 1, link 2, so on up to link L. Correct? Therefore, the probability, let me call, when is this system in deep fade? The system is in deep fade. Can someone tell me when is the system? When is the system in deep fade? Can someone tell me when is this system? When can we say that this system is in a deep fade? Can someone tell me when is the system in a deep fade? When is the system? When is it in a deep fade? If I have L links, when is the system in a deep fade? If I have single link, obviously the system is in a deep fade if one of the links is in a deep fade, right? There is only one link. That is because there is one transmit antenna, one receive antenna, so that the system, the wireless system is in a deep fade if one of the links is in a deep fade. If I have L antennas, when is the system correspondingly, when is the system in a deep fade? Can someone tell me when is the system in a deep fade corresponding to a L antenna system? When is the system in a deep fade corresponding to an L antenna system? Each signal power is less than the noise power, correct? That is basically each of the L links is in a deep fade. That is the link corresponding to receive antenna 1, link corresponding to receive antenna 2, so on up to link corresponding to receive antenna. All the gains are less than 1 over SNR. That is correct. That is all the gains G1, G2, GL are less than 1 over SNR, which means each of the links is in a deep fade. Because even if one link is not in a deep fade, then communication is possible between the transmitter and receiver. Therefore, the system is in a deep fade, that is communication is not possible only if all the L links are in a deep fade. Now probability of each link in a deep fade arises as 1 over SNR. Therefore probability of L links which are independent in deep fade is 1 over SNR into 1 over SNR into 1 over SNR, which is equal to 1 over SNR to the power of L. Therefore, to summarize, basically what we are seeing is a very interesting phenomena when we have multiple receive order. There is a diversity gain. There is a diversity increase in the diversity order of the bit rate. Why is this diversity order increasing? Because as the number of links are increasing, the probability of deep fade is decreasing. As the number of links, which are independent paths between the transmitter and receiver, as the number of independent links is increasing, probability of deep fade is decreasing because you are increasing the signal reception diversity. What is the meaning of diversity? Diversity is mean, yeah, I will do a recap. I will also take some questions because I have some time. I will take some questions and I will do a recap. The diversity is basically increasing because the probability the links are basically in a deep fade. Yeah, I'm going to take some questions, a couple of questions. PSGCT, they are asking what is the maximum, what is the factors dictate the choice of L. As I said, the choice of L depends on the standard, it depends on the system, it depends on how much complexity of the system is. It is very complicated the choice of L is not very straightforward, right? So it depends on the cost of the system, it depends on the size of the system. Typically base stations have anywhere, modern base stations such as LTE have anywhere up to 4 to 8 antennas is proposed. In handsets, about 2 antennas is proposed. In Wi-Fi, etc. Again, on the Wi-Fi cards, etc. there are 2 antennas that are being proposed. On Wi-Fi access points, there are about 4 antennas that are being proposed. Anyone else? Does anyone else have any question? Any other question? So the choice of L depends on complicated is a complicated choice. It depends on the cost. It depends on the system complexity. Is also depends on, correct, it also depends on the distance. The spacing between antennas has to be as large as possible. Typically it has to be greater than or equal to the half the wavelength, that is lambda by 2, and typically half the wavelength at 2.4 gigahertz, the wavelength is approximately about 5 centimeters, 5 to 10 centimeters. The distance has to be basically approximately about 5 centimeters, 5 to 10 centimeters per between antennas. That is correct. So the choice of L depends on the, it does not depend on the distance. I think LMI, I don't know, it does not depend on the distance between the TX and RX. No, it does not depend on the distance between TX and RX. It depends on inter antenna spacing. It depends on the spacing between the antennas. It depends on the spacing between the various antennas. Can someone ask another question? Does anyone have any other question? We have tried to cover thoroughly what is the impact of diversity. See, my idea is to try to give you as much as possible, as much knowledge as possible regarding the fundamentals, so that you can go back and read some of the textbooks and gain knowledge of the advanced concepts. Because this class is limited and also the audience of the class is diverse, I cannot include several advanced concepts such as probably MIMO, OFDM. I will still try to cover some of the basics of MIMO and OFDM, but MIMO and OFDM require much advanced theory. That is basically what is MIMO communication, how do you compute the bit error rate of MIMO communication, so on. That requires a bit advanced theory. I've realized that because of the limited time, that is because of fewer number of lectures, and also because of the diversity of the audience, because I have a large number of students belonging to various backgrounds, belonging to various years and various backgrounds. For me, it is very difficult to cover a very advanced concept, typically what we cover at IIT here. So therefore, I'm covering it rigorously, but I'm covering several basics. For instance, diversity is a very important concept in wireless communications. I hope everyone has understood the importance of diversity. GIT is asking me a question, what about the direction of antennas? The direction of antennas, it depends the direction of, here we have not assumed any specific direction of antennas, we have assumed omnidirectional antennas. But direction of antennas can also be, there can be sectorization, that is you can have sectoral deploy antennas by the sector, and also basically you can have directional antennas which further. But you can see clearly, if I have multiple antennas, I don't need directional antennas, because with multiple antennas itself I can appropriately choose, depending on, of course we have not looked at the theory of that. With multiple antennas, with omnidirectional antennas itself, we can choose a particular direction, that is we can beamform in a particular direction. These are known as smart antennas, right? These are known as smart antennas. Smart antennas means that I don't really need directional antennas, but with multiple omnidirectional antennas itself I can beamform in an appropriate direction. These are known as smart antennas, or these are known as, also known as antenna arrays. Another word for this is an antenna array, and this is also basically known as array processing. Does anyone have questions? Yeah, go ahead please. If you have any questions, this is a good time. Go ahead please. We have some time, so we can take some questions. Yeah, someone requested me to do a recap. Looks like it's not possible to do a recap now, but I'll do a recap in the next lecture, and then we'll move on to characterization of the wireless channel. So basically this completes the module on diversity, and we will move on to characterization of the wireless channel, which means we have to talk about parameters of the wireless channel, such as what is the delay spread, coherence bandwidth, what is the Doppler. Of course, Doppler is also important. Digital beam, yeah, this is exactly digital beamforming. Digital beamforming is basically beamforming in a particular direction. That is basically not, this is also electronic beamforming, that is not physically steering an array. See, what we do in digital beamforming is we don't physically steer the array in a particular direction, but using the antenna weights we choose a particular direction. The theory is a bit more involved. I don't know if I'll be able to cover that theory, but digital beamforming or electronic beamforming means rather than steering the array physically, you are using electronic weights to basically choose a particular direction. Regarding how many more classes, I don't know exactly, because we missed 2 classes because of technical issues. I will try to cover that. What I'm trying to see is I'm trying to see if I can get a slot between 8 and 9, because that is the slot that is most convenient for me here at IIT Kanpur, as I don't have a studio. So let us see, there might be a couple more classes, and well, on Holi I don't think there will be any lecture, because on public holidays I don't think there is any lecture, but please confirm from the this thing. As for me, of course I will be on a holiday, so for me it will be difficult of course to deliver a lecture on Holi, but I think officially also on Holi there will be no lecture, but please confirm this from the organizers, from that is QEEE, that is the team from IITM, they will confirm the exact policy. I think on Holi there are no lectures. And how many more classes, that also I am not clear about it. There are a couple of classes. My guess is there are about 4 to 6 classes remaining. Yeah. Anything else? Any other questions? I will do a recap in the next lecture. That's what I said, because I think we are running out of time. I will do a recap in the next lecture. In the next lecture, I will do a recap at the beginning. Okay, thank you, thank you. I think everyone, I think, yeah. So I hope everyone is understanding KNM Youth. I am glad that you are able to understand. Thank you very much. As I said, my aim is the following thing regarding this course. My aim is basically to reach as many students as possible throughout and across the country, and each of them, help each of them as much as possible to whatever extent is possible. Remember, this is not, yeah, regarding yeah, remember, because this is not possible because you know all of you are not here at IIT, and it's something, teaching on the class is something different. So with these limitations, whatever is possible, I'm trying to make my best, and of course this is a great system, so it looks like I'm able to convey some ideas across. And considering the various backgrounds, I have to slightly temper down the material a little bit, reduce the complexity a little bit. But my idea is to give you a solid knowledge of the fundamentals of wireless communication, especially regarding concepts such as fading diversity. Yeah, now regarding the textbook, I have already suggested the textbook several times. That is also given on the course website, but let me also once again, let me also suggest that the textbook is Fundamentals of Wireless Communication. Fundamentals of Wireless by David J. and Wireless by Andrea Goldsmith. These are the 2 textbooks. Yeah, there is an option to view missed lecture videos. The missed lecture videos, they are available online. For instance, if you go into the library for the course, you can view the lectures, right? If you are having difficulty, then please contact the QEEE team. They will help you locate. All the lecture videos are being recorded, right? So all the lectures videos are being recorded, and including lectures and notes are also available online. So please take contact. If you are not able to view them, please contact the QEEE team. Yeah, please contact the QEEE team. Okay, so I hope that, so with that I will conclude this session. So we have completed an important aspect, that is diversity. I hope everyone appreciates now what is the importance of diversity to overcome the fading aspect of wireless communication system. From the next lecture we will talk about the fading, we will talk about the wireless channel characterization such as delay spread, especially Doppler, that is what happens when a mobile is moving, what is the Doppler effect, how do you characterize the Doppler, what is the impact of Doppler on wireless communication. So with this, I will conclude this lecture. Thank you. Thank you everyone for listening patiently. Thank you.